Hello, everyone. My name is Matthew Webb, and I'm a student physical therapist with a CSCS and a BS in nutrition science. Today, I'm going to be talking about thiamine or vitamin B1. This is going to be the first in a series of educational videos intended for healthcare professionals to help us in direct access healthcare fields become more adept at identifying nutritional deficiencies so that we can get patients presenting with one of these diseases the help that they need. So, without any further ado, allow me to present to you vitamin B1. So, firstly, we're going to go into the very basics behind deficiency of thiamine. Then we'll break down the science behind why patients are presenting the way that they do. Then I'll give you some takeaways to help you identify this disease. When a patient has thiamine deficiency, you may find cardiac signs or neurosigns, or potentially both. And we'll go further into the science behind these presentations and the risk factors later in this presentation. But I just wanted to provide you an idea of what we're going to be getting into in this lecture right here. Let me begin this slide with an apology. In this lecture, I'm going to be talking about a decent bit of biochemistry, and I may elaborate on some ideas that some of you don't need me to elaborate on. So, with that being said, this slide probably looks familiar to most of you. This is the citric acid cycle, or Krebs cycle. This model in particular shows where the B vitamins act as enzyme cofactors to fuel this process. As many of you likely know, the Krebs cycle and electron transport chain combo are the most efficient processes in our body for making ATP. Both those processes are referred to as aerobic respiration because they require oxygen to function. As we can see, there are a lot of organic molecules that come together to make this process run smoothly. When one of these molecules is lacking, our body's aerobic respiration efficiency suffers. And as we can see at the beginning of this illustration, vitamin B1 is already an enzyme cofactor necessary just to create the acetyl CoA that's required to begin the citric acid cycle. So, in the case of B1 deficiency, to create a bit of an analogy here, if this were a race, it'd be like we got shot in the foot right at the starting line. So, this diagram right here is essentially ground zero for the calamity that is thiamine deficiency, which, keeping with the nuclear bomb analogy, like radiation, the effects of this are far reaching, seeping into and infecting the surrounding systems, thus causing the rest of the problems we will soon see with beriberi, aka thiamine deficiency. The big systems impacted by this are the nervous system and the cardiovascular system. Let's start with the nervous system. We know the nervous system is impacted in dry beriberi. Now, the central nervous system certainly is impacted as well. However, even though upper motor neurons may be impacted, we see more issues with lower motor neurons and peripheral nerves. It is assumed that the reason dry beriberi usually results in lower motor neuron signs is because the long axons that our peripheral nerves have make them more susceptible to metabolic disruptions, such as the decreased aerobic respiration we see in thiamine deficiency. Note, myelin synthesis can also be impacted by thiamine deficiency, which is also no good for our nervous system, and that can kind of be seen to the right, bottom right of this slide. Here's a cardiomyocyte action potential, which we will eventually come back to after I give more context to how thiamine deficiency impacts the cardiovascular system. So, much like the nervous system, the main cardiovascular issues associated with thiamine deficiency are related to the increased anaerobic respiration and decreased aerobic respiration. In the middle, I have a pretty thorough illustration of glycolysis, and to the right, I have a more simplified version. To show you what's going on, we'll use the simplified version in the top right. So, typically pyruvate, after being produced at the end of glycolysis, will go on to be turned into acetyl CoA for the citric acid cycle, as can be seen by the red arrow going from pyruvate to acetyl CoA. However, since that may not be an option with thiamine deficiency, instead it is turned into lactate for the purpose of turning NADH, that you can see being produced by glycolysis, back into NAD plus so that we can reuse it to begin glycolysis all over again. Now, a really simple explanation for why this could be a bad thing would be to feed into a lie that all of you have likely already heard. And that is tempting because even some scholarly articles will use this as their explanation. However, I figured since this video is intended for healthcare professionals, we of all people should at least have our facts straight. Let me just begin by dispelling the myth of lactic acid accumulation. Cellular respiration does not produce lactic acid. It produces lactate, as you can see here. And lactate is a much more stable molecule than lactic acid, so it's not going to just spontaneously turn into lactic acid either. So lactic acid isn't something that you should be accumulating in your body to the extent necessary to cause metabolic acidosis. And some of you may know where I'm going with this. Metabolic acidosis is actually caused by accumulation of hydrogen protons, which are acidic. So, where do those hydrogen protons come from? That is the question we should be asking. Some people may tell you it's glycolysis that causes excess hydrogen protons during anaerobic respiration, which makes sense at first when you look at the simplified glycolysis formula. We have two hydrogen protons as end products. However, we have to then go through lactate fermentation, which according to the simplified lactate fermentation formula, we actually use up two hydrogens. So from an overly simplified perspective, we're basically hydrogen neutral at this point. Because this reaction should theoretically happen twice, thus recycling those hydrogens, this leads us to the currently accepted mechanism of hydrogen proton induced metabolic acidosis, which is ATP hydrolysis. The formula for that can be seen down on the bottom of the slide. As we can see here, the hydrogen proton is hanging out as a product of this reaction. So, what are we going to do with it? That is a question that anaerobic respiration doesn't really have an answer for, whereas aerobic respiration does. So let's dive into that statement and see why using aerobic respiration makes us a little more resistant to metabolic acidosis than does anaerobic respiration. So, in aerobic respiration, aka the Krebs cycle and electron transport chain, the Krebs cycle actually produces even more hydrogen protons, approximately 3 per turn, and several hydrogen donors in the form of NADH or FADH. As it turns out, that's essentially its main purpose because in the membrane of mitochondria of a human cell, there are between 1,000 and 5,000 of these small motors called ATP synthase, which is that structure with the rainbow of colors in the second illustration. That motor is spun like a water wheel to very efficiently create ATP. So, in aerobic respiration, our body actually wants hydrogen protons to act like water spinning a water wheel to produce energy. This is one reason why metabolically demanding tissues such as our heart will be more likely to enter a state of metabolic acidosis if it is forced to rely more on anaerobic respiration, where hydrogen protons don't get to serve the purpose of energy production, compared to aerobic respiration, where they're actively being recycled in the electron transport chain. All right, let's go into the bigger picture impacts of thiamine deficiency on the cardiovascular system. Firstly, through a series of cellular changes, the metabolic acidosis we talked about in previous slides leads to inhibition of fast sodium channels needed for rapid depolarization, aka phase zero, which is in green on the cardiac action potential illustration. This can cause arrhythmias. Secondly, like we established in the last few slides, glycolysis is less efficient than aerobic respiration. So AMP, that's adenosine monophosphate, which is the phosphate depleted version of ATP, our cell's energy. Those AMP levels begin to rise as our body fails to replenish ATP. Technically, ADP also accumulates, but it's AMP that matters most for heart function because AMP binds to a protein complex to become AMPK. This upregulates glycolysis and also causes vasodilation. And that vasodilation concept we will come back to later. Usually, we like AMPK as when it is elevated just from exercise, it can be cardioprotective and is also associated with some good exercise induced gene expression. However, too much of a good thing is usually a bad thing. And when we're going through an energy crisis like we are here, we get too much AMPK for too long. Due to that long term vasodilation it causes, the heart beats harder to maintain blood flow and overcome decreased peripheral resistance from that vasodilation. This level of cardiac output cannot be maintained forever. Thus, it is called high output heart failure. A note here is that it is often accompanied by tachycardia. Here are some risk factors you can look out for. Medications such as diuretics due to vitamin B1 being a water soluble vitamin causes extra excretion of the vitamin, which can increase risk. Antibiotics, particularly metronidazole class drugs, can change in the gut to become structurally similar to thiamine. So it literally blocks thiamine transporters, acting like an antagonist to thiamine absorption. Anticonvulsants taken for things like epilepsy can impact the metabolism of multiple B vitamins, and it's been known to occasionally cause different B vitamin deficiencies. Proton pump inhibitors can cause something called hydria, which is decreased hydrochloric acid in the stomach. That alone could impact B vitamin absorption. However, this is known to cause bacterial overgrowth in small intestines, which competes with you for thiamine absorption. Alcoholism causes something called Wernicke-Korsakoff syndrome. This is functionally the same thing as beriberi. Alcoholism's impact on B1 deficiency is essentially threefold. Alcohol impairs thiamine absorption due to intestinal damage. Thiamine is used and used up in alcohol metabolism. Alcohol acts as a diuretic, which increases urine production, thus increasing thiamine excretion. Some subjective questions we can ask to see if patients have any risk factors would be what medications are you taking? And make note if they are taking metronidazole, class antibiotics, anticonvulsants, or PPIs. Any alcohol consumption, then of course figuring out what their alcohol use looks like because up to 80% of people with severe alcohol use disorder experience thiamine deficiency. As for any numbness or tingling, then figuring out whether multiple extremities are impacted or just one. There's a good chance that with this disease, they could be experiencing it in more than one extremity. And of course, note that other diseases with correlation to thiamine deficiency are Alzheimer's, Huntington's, Parkinson's, amyotrophic lateral sclerosis, or ALS. Clinical exam in vitals, we could see tachycardia. In the integumentary system, we could see pitting edema. For reflexes, they'd potentially have hyporeflexia, which would likely be bilaterally, but could start unilaterally. For sensation testing, sensation loss would likely present following peripheral nerve patterns more often than nerve root and dermatomal patterns. This would also likely present bilaterally. And muscle performance screening, as well as MMTs, could present with weakness bilaterally. If you see this combination of cardiac and neuroscience paired with the subjective findings in the prior slide, then thiamine deficiency is something you may want to consider for your differential diagnoses. To summarize the what, how, and why behind patient presentation with thiamine deficiency, the nervous system can be detrimentally impacted with lower motor neuron signs usually appearing first. This is due to combination of myelin degradation and energy deficits. Myelin degradation is due to myelin synthesis being a metabolically demanding process requiring substantial ATP contribution. The Krebs cycle is impaired because thiamine is an enzyme cofactor necessary to begin aerobic respiration. Lower motor neurons are impacted to a greater degree because of their long axons being more metabolically demanding. The cardiac system is also negatively impacted through metabolic acidosis, impaired cardiac action potentials, and heart failure. Without aerobic respiration to recycle hydrogen protons and create more energy, hydrogen is unable to be used for ATP production, so it builds up, causing metabolic acidosis. During metabolic acidosis, fast sodium channels that are required for the first phase of a cardiac action potential, necessary for depolarization, are inhibited, which can cause arrhythmias. During an energy deficit, like when aerobic respiration is impaired, AMP builds up, which binds to a protein complex called AMPK. AMPK causes vasodilation. This is fine in the average person when caused by exercise. However, the heart has to work harder with chronic vasodilation, which is why tachycardia is often a finding in this deficiency. The heart can't keep up at that pace forever, thus, thiamine deficiency can cause high output heart failure. And here are my resources. Thank you for watching. Note that I am making these presentations during a pretty busy semester, so I'm liable to make some mistakes. If so, let me know in the comments, and if your correction checks out, then I'll either add it to the video description or I'll pin your comment. If that is a thing you can do on YouTube, I don't actually know yet. If you learned something from this video and you want to learn more, continue on to my riboflavin video or vitamin B2.